Alright guys, your essential question for today is, how do we find the asymptotes of rational functions? And you have three vocabulary words: horizontal asymptote, and remember horizontal means that it's going left and right; vertical asymptote, which remember it means going up and down; and then rational function. Alright, if you remember a couple of days ago when we were studying the parent graphs, there were six main functions that I said that we would cover. One of those was the rational function, or 1 over x. And if you remember, the rational function looks like this. Now, I didn't specify it then, but you can clearly see that there are some asymptotes on my graph. In fact, there is a horizontal asymptote right here, so I'm going to put that horizontal asymptote at y is equal to 0, or in other words, the x-axis. And remember, an asymptote is it's an imaginary line where your function gets closer and closer and closer to, but actually never touches or crosses. So as you can tell, the function gets closer to the x-axis on either side, but it's never going to intersect there. Not only is there a horizontal asymptote at y is equal to 0, but there's also a vertical asymptote at x is equal to 0. So as you can tell, the function gets closer and closer to the y-axis, but it actually never crosses or touches. So for that parent function, there are vertical and horizontal asymptotes. Now, if you remember, any parent function, whether it be the cubic, quadratic, square root, you can transform those parent functions by manipulating the function. For example, you could move a graph up by adding a constant, or move a graph down by subtracting a constant, or move a graph left or right by changing the number inside of the function, inside of the square root, or inside of the absolute value. What we're going to do for our first example is we're going to use this parent function to transform and move the graph depending on what the situation is. So let's go ahead and look at our first example. And for the first example, there are two separate problems here. It says use the parent graph to graph the function. Both of these are rational functions. So I'm just going to go ahead and just remind us that the actual parent function for the rational function is this. Alright, now whenever we do these graphs, it doesn't have to be exact. I just want to get an idea of what these graphs look like. So let's look at the first one. It says g of x is 1 over x plus 5. I don't want you to get this confused with 1 over x plus 5. These are two separately distinct graphs. For example, this one, I would simply take my rational function and move it up 5. This is not with the plus 5 on the outside of my fraction. It's with on the inside of it. So because of that, I know that this means I'm going to have a horizontal translation. I'm going to move it either left or right. And since this is a positive 5, I'm going to think the opposite. So I'm going to move 5 units left. So if I were to literally take this parent function and literally just move it 5 units left. Well, when I move this parent function, I'm going to draw it right here. This is the original function right here. If I were to take this and move it 5 units left, right now, the vertical asymptote is at 0, but if I move that 1, 2, 3, 4, 5, now my vertical asymptote is here at 5. And I didn't move it, the graph up or down, so I'm still going to have this same shape right there. It's all I've done is just pick the graph up and moved it 5 units to the left. Alright, so I'm going to redraw this so it's not both of them all on the same graph, but what the graph would look like would simply be 1, 2, 3, 4, 5. There would be a vertical asymptote at negative 5. The horizontal asymptote is still at 0 because I didn't move the graph up or down, and then my function is going to still have that basic shape, just like that. Alright, I just want to confirm this by using my graphing calculator. So I'm in my graphing calculator. I'm going to hit Control Divide to make a fraction, and I'm going to put 1 over x plus 5. And as you can tell, the graphing calculator does show that there is a vertical asymptote at negative 5. So I literally, and actually I will show you the basic function too, Control Divide 1 over x. So in red, that was the original function, and then the 1 over x plus 5, we shifted it 5 units to the left, so that's the function in blue. Alright, let's take a look at the second function. Alright, for this one, it has negative out in front, and then 6 over x plus 2 minus 4. The first thing I notice is that I have a vertical translation of 4 units down. So that horizontal asymptote that was at 0 is now going to be at negative 4. So I'm just going to go 1, 2, 3, 4. So now here's where my horizontal asymptote is. I also noticed that there is a horizontal translation, and since that's x plus 2, I know it's going to be 2 units left. So I'm going to go 2 units left, and so my new vertical asymptote is going to be right there. Alright, so notice I've got my 4 quadrants right here. And then the other thing that I do notice is that this is a negative, so it's going to reflect our pattern across the y-axis. So originally when it was up, if you remember, the original rational function looks like this. So if we reflect that, that means this piece is going to be over here, and this piece is going to be over here. So what I'm going to have is, I'm going to have this function in blue. So there and there. And again, that's just a rough sketch, a rough idea of what this function looks like. So we're going to do the same thing. We're going to take a look at it in our graphing calculator. So let's type this in our graphing calculator. We're going to have negative, and then Control Divide, and then 6, and then that was x plus 2, and then off to the side minus 4. So I typed it in, I hit enter, and let me just move my graph just a little bit so you can see it. But if you notice, there is a vertical asymptote here at negative 2, and there's also a horizontal asymptote here at 1, 2, 3 at negative 4. But notice it is reflected, as we talked about, across the y-axis, unlike the traditional. And in fact, I'll go ahead and let you see the original. Here it would be the original rational function, just 1 over x in pink. But notice that it's not only reflected, but it's also moved down and to the left. So it did exactly what we knew it was going to do. Alright, let's go ahead and take a look at another example. Now notice for this example it says determine the asymptotes for the graph of f of x equals 3x minus 1 over x minus 2. Notice it doesn't want you to graph it, but we'll actually confirm our answer by graphing it in our graphing calculator. Alright, now remember, just like your essential question, there are 2 types of asymptotes that we look at, horizontal and vertical. Now I have a preference for finding the vertical asymptotes first. So let's start there. The way that you find the vertical asymptotes for a rational function is wherever the function is undefined. And remember that a function, a rational function, is undefined if the denominator, I spelled that wrong, denominator is 0. So in other words, whatever number makes the denominator 0, then that is where the function is undefined, and that's where there could be a vertical asymptote. So what I'm going to do is I'm just going to look at my denominator, x minus 2, and I'm going to just set that equal to 0. So x minus 2 is equal to 0. And I'm going to solve this for x. X is equal to 2. So this means that there is a vertical asymptote at x is equal to 2. Okay, alright, so then I'm just going to draw this situation. So at x is equal to 2, 1, 2, there is a vertical asymptote right there. Alright, now, horizontal asymptote. This one's a little bit harder, but there's actually just some rules for it. So once you have the rules, you'll be okay. Alright, so what you look for with the horizontal asymptote is you look at the degree in the numerator and denominator. Okay? The degree. Remember, the degree is the highest exponent. So in this case, the highest exponent in the numerator is 1. The highest exponent in the denominator is 1 also. Okay, so there are basically 3 scenarios here. So let's start off with the first one. If the degrees are the same, then your asymptote, then the horizontal asymptote is your coefficient. Okay? If they're the same, which that would fit this scenario. Now the coefficient in the numerator is 3, the coefficient in the denominator is 1, so that means that I'd have a horizontal asymptote at y is equal to 3 over 1, or just simplify that, y is equal to 3. So that's my first scenario. The second scenario is if the degree in the numerator is higher. Now, if this happens, then there is no horizontal asymptote. So that one's nice and easy and clean. The third one is if the degree is higher in the denominator, then the asymptote, the horizontal asymptote, is simply the x-axis, or y is equal to 0. So in our case, though, we said that the horizontal asymptote was at 3. So 1, 2, 3. And so we have a horizontal asymptote right there. And again, this is a rational function, so I would know that it would look something like this, hopefully. And we're just going to confirm it to see if that's the case by plugging it into our graph and seeing if that's true. So let's take a look. Alright, so I'm going to plug it in. I'm going to hit Control, Divide, and I'm going to do 3x minus 2, and in the bottom, x minus 2. Actually, I think that was 3x minus 1. I'm sorry, 3x minus 1, not 3x minus 2. Okay, and then hit Enter. And then, sure enough, I think that is what I drew right here. Okay, let me go back and look at it. Alright, so as you can tell, there is a horizontal asymptote at 1, 2, at 3. There's a horizontal asymptote there. In fact, I'll draw that. There is a horizontal asymptote 1, 2, at 3. And there's also a vertical asymptote at 2. Whoop, 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 whoop. Do not drink and derive. Anyway, alright, so I'm just confirming what we found mathematically. So again, guys, you don't have to use your graphing calculator to ever find the vertical or horizontal asymptotes, but using your graphing calculator to confirm it is a great, great tool. All right, let's take a look at another example. This time it wants you to identify the vertical and horizontal asymptotes of x squared minus 4x plus 3 over negative 3x squared plus 12. All right, now that we've got the three rules for the horizontal asymptotes, I think that's going to be the easiest to manipulate. So notice that the degree in the numerator is 2, the degree in the denominator is 2, so it's the same degree. So I'm just going to look at the coefficients. The coefficient in the numerator is 1, the coefficient in the denominator is negative 3, so my horizontal asymptote is at 1 over negative 3. I'm just going to write that as negative 1/3. So there's my horizontal asymptote. My vertical asymptote is going to take a little bit more work. Remember, the vertical asymptote occur wherever the denominator is 0, or wherever the function is undefined. So I'm going to have negative 3x squared plus 12. I'm going to set that equal to 0. I know it's a quadratic, so I'm going to have two answers. So if I try to solve this for x, I'm going to have negative 3x squared equals negative 12. I'm going to divide by negative 3, so that's going to give me 4. And then I'm going to take the square root, and so that's going to give me plus or minus 2. So I have two vertical asymptotes. And so now I'm going to try and draw the scenario. So I've got a vertical asymptote at positive 2, so right here, and a vertical asymptote at negative 2, so right there, and then I also have a horizontal asymptote at negative 1/3, so right there. Now, notice, guys, that this is not a rational function, because you notice it's squared and squared, so it's not your traditional rational function. All I'm trying to do is see where those asymptotes are. Now, I'm going to try and confirm this to make sure that the asymptotes are where we said they were going to be. So let me pause and pull out the graphing calculator. Alright guys, I went ahead and typed it into my graphing calculator, x squared minus 4x plus 3 over negative 3x squared plus 12, and I hit enter, and sure enough, there is my function. Alright, so just to confirm, you notice that there is an asymptote, a vertical asymptote at negative 2, so right there, and then at positive 2, so right there. So sure enough, our two vertical asymptotes are there, and then notice that this is negative 1, and so if you notice, the function on the left-hand side gets closer and closer and closer to that negative 1/3, but doesn't cross it, and even over here it gets closer and closer and closer to that negative 1/3 over here and doesn't cross it either. So that is a horizontal asymptote of the function. All right, so I was just confirming that those asymptotes are there. All right, let's go back to our problems and let's look at another example. All right, so let's do this one, and I'm not going to confirm it with the graphing calculator this time. But let's start off with the easy one. Let's do the horizontal asymptote. Notice that the degrees are the same, so just look at the coefficients. So then my horizontal asymptote is going to be at 1 over 1, or simply 1. Y is equal to 1. So there's a horizontal asymptote there. My vertical asymptotes are wherever the denominator is equal to 0 or undefined. So I have this, and I notice that they have an x in common, so I'm just going to solve this by factoring. So I'm going to factor out an x, and that's going to leave me x squared minus 4. And then I notice that this is a difference of two squares, so I'm going to factor that into x plus 2 and x minus 2, and set each one of these equal to 0. So I'm going to have x is equal to 0, x plus 2 is equal to 0, and x minus 2 is equal to 0. So I get three vertical asymptotes. X is equal to 2, x is equal to negative 2, and x is equal to 0. And then I know I said I wasn't, but I'm going to go ahead and confirm this one as well. Alright, and so I went ahead and typed it into the graphing calculator, and sure enough, let me go back to it. There we go. And then, sure enough, we have our vertical asymptote here at 2, and we also have a vertical asymptote at negative 2. Now, the one that might be surprising is that if you remember a while ago, we said that we we're going to have one also at 0. At 0. Well, there's one thing I want to go over right quick. With this function, if you notice, in the numerator, what is my GCF that they all have in common? They also have an x in common. So I could factor the numerator with an x coming out, and that would leave x squared plus 3x minus 4. And in the denominator, we factored this out to be x and x minus 2 and x plus 2. If you notice, they have an x in common. So anytime there is a common factor between the numerator and denominator, it won't be a vertical asymptote, but it will be a point discontinuity. All right, let me just go back and confirm that. Notice that these factors do not match up in the numerator, so that is why they are vertical asymptotes at 2 and negative 2. But the x factors they have in common, so that's why at 0 right here, there is no asymptote there. But if I were actually going to go to Menu, Trace, Graph Trace, if you notice at 0, even though there's not a vertical asymptote, it is undefined at that point. And that's what we call, if you remember, a point discontinuity. Okay? So just remember that. Let me go back to it. Anytime there's a common factor between the numerator and the denominator, it won't be a vertical asymptote, but it will be a point discontinuity. And again, you'll be able to confirm that by using your graphing calculator as a tool to help you see if your answer is confirmed or not. All right, let's look at one more example. Okay, for this one, I noticed that I'm going to do my horizontal asymptote first. I noticed that the degree in the numerator is bigger than the degree in the denominator. So I'm just going to go back to those rules right quick. And if the degree is higher in the numerator than in the denominator, there is no horizontal asymptote. So for this problem, I'm just going to put there is no horizontal asymptote. And then we'll confirm that in a second. But for now, let's go ahead and find our vertical asymptotes. So again, set the denominator equal to 0. 3x minus 12 is equal to 0. Solve it for x, and so that's going to give me x is equal to 4. So hopefully I'll have a vertical asymptote at 4. So let's check that right quick. So that's x squared minus 2. So let me type that in the graphing calculator. X squared minus 2, and in the denominator, 3x minus 12. All right, and so there is my graph. Let me just go ahead and move this function out of the way so you can see it. And then sure enough, at x is equal to 4, 1, 2, 3, 4, there is a vertical asymptote. And there is no horizontal asymptote for this because it will continue to go down this way and it will continue to go up that way. So there's no horizontal asymptote for this one. Okay, that's it for today's lesson. If you need to go over and review this, then by all means go back and watch it over again, and we will continue to practice this for the next lesson.